We will now discuss the solution of a problem from the section Linear Algebra. The problem is based on the concepts of rank of a matrix. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022 and it is from the part C. The given question is, let A be an m by n matrix such that the first r rows of A are linearly independent and the first s columns of A are linearly independent, where r less than m and s less than n. Which of the following statements are true? We are given four options. Option 1, the rank of A is at least the maximum of R comma S. Option 2, the submatrix formed by the first R rows and the first S columns of A has rank minimum of R comma S. Option 3, if R less than S, then there exists a row among the rows r plus 1, r plus 2, etc. up to m, which together with the first r rows form a linearly independent set. Option 4, if s less than r, then there exists a column among the columns s plus 1, s plus 2 up to n, which together with the first s columns form a linearly dependent set. We are given a matrix A whose order is m by n, m rows and n columns. It is given that the first r rows of A are linearly independent and the first s columns of A are linearly independent, where r less than m and s less than n. Then we have to decide which of the following statements are true. Agreed? We now discuss the solution of the problem in detail. We have an m by n matrix. We know that the rank of A is equal to row rank of A is equal to column rank of A. Agreed? Given that the first r rows of A are linearly independent, therefore row rank of A is at least r, greater than or equal to r. But that implies row rank is equal to rank of A is greater than or equal to R. We are also given the first S columns of A are linearly independent. That will imply the column rank of A is at least S. From that, it follows the rank of A is greater than or equal to S. Agreed. So, from the facts that the first r rows of A are linearly independent, the first s columns of A are linearly independent. From that, we get rank of A greater than or equal to R and rank of A greater than or equal to S. So these are the two facts what we got, and let's get into the option 1. Now, option 1 says the rank of A is at least maximum of R comma S. Yes, this is true. How? Now, rank of A greater than or equal to R and the rank of A greater than or equal to S. Correct? This will imply the rank of A is greater than or equal to the maximum of R comma S. Yes, this is true. This is true. So then that means the rank of A is at least the maximum of R comma S. Agreed. That means the statement what is given in option 1 has come now. Therefore, the option 1 is true. Thus, the option 1 is true. Now, let us discuss the remaining cases in the next slides. We now take the option 3. The option 3 says, if R less than S, then there exists a row among the remaining rows R plus 1, R plus 2, M, up to M, which together with the first R rows form linearly independent set. Okay, let's see. Let R1, capital R1, capital R2, capital RR be the first R rows that are linearly independent. It is given R less than S. Let R less than S. We have the rank of A is greater than or equal to the maximum of R comma S. This is true, which we have established in option 1. We use it. Therefore, the rank of A greater than or equal to maximum of R comma S, but R is less than S, the maximum of R comma S will be S. So, this will imply the rank of A is greater than or equal to S. Yes. R less than S means S greater than R. This will imply the rank of A greater than or equal to S greater than R. That means the rank of A is greater than R, where R is less than M, strictly less than M. Therefore, the rank of A is at least R plus 1. The rank of A greater than R, but R less than M. Therefore, the rank of A is at least R plus 1. So, this says what? The row rank of A is at least R plus 1. This says what? Besides you are given the first R rows which are linearly independent, we are going to get one more row which is linearly independent with the first R row, linearly independent rows. So, this means there exists a row, say Ri, in the remaining rows, that is the set consisting of RR plus 1, RR plus 2, Rm, such that the set of rows consisting of the first R rows and this row Ri is linearly independent. So, this shows that the option 3 is true. Agreed? Agreed. Now, let's get into the next option. Option 2. The submatrix formed by the first R rows and the first S columns of A has rank minimum of R comma S. We have an M by N matrix in which the first R rows are linearly independent and the first S columns are linearly independent, and it is further given R less than M and S less than N. Let us take the submatrix. Let capital B be the submatrix formed by the first R rows and the first S columns of A. That means it is an R by S submatrix. Now, the rank of B is equal to row rank of B, yes. And how many linearly independent rows are there? R. So, the rank of B is equal to row rank of B is equal to R. Similarly, rank of B is equal to column rank of B is equal to S. Agreed. Agreed. Since the rank is unique, whether you do it row rank or column rank, they must be all equal. Therefore, R must be equal to S. Then the rank of B is equal to the minimum of R comma S. Because it is either R or S, you will get the rank of B is the minimum of R comma S. When this is true? When R is equal to S. When R is equal to S. So, the result is true only when R is equal to S. What happens when R not equal to S? If R not equal to S, then the row rank of B, which is R, not equal to column rank of B, which is S. And this is not true. Whenever row rank and column rank are there, both are equal. The common value is the rank of the matrix. And it is not true. And it is not true. So, thus the statement given in option 2 does not hold. Does not hold. Now there are no conditions given on R and S. On R and S, there are no conditions given. When there are no conditions, and the first we have proved that the result is true when R is equal to S, and definitely you have to talk about when conditions are not given R and S. When R not equal to S, what happens? Then the statement given in option 2 does not hold, because it is not possible. It's not possible. So the option 2 is not true. Therefore, the option 2 is not true. So we are left with the fourth option. If S less than R, then there exists a column among the remaining ones, S plus 1, S plus 2, S up to n, which together with the first S columns form linearly dependent set. Dependent set. Agreed. Now the proof, up to some extent, it is the same proof as that we have given in option 3. Let C1, C2, Cs be the first S columns that are linearly independent in the matrix A. And it is given S less than R. We take it. Let S less than R. We have rank of A is greater than or equal to maximum of R comma S, which is true, which we have established in option 1. Therefore, S less than R, the maximum of R and S will be R. Agreed. The rank of A is greater than or equal to R. But S less than R means R greater than S. The rank of A is greater than or equal to R greater than S. This means the rank of A is greater than S, but S is less than N. Therefore, rank of A is at least S plus 1. Okay? So, the column rank of A is at least S plus 1. Up to this, the same proof, similar proof what you have done in option 3. So, there exists a column, at least one more column, let us say Ci, from the remaining columns, so Cs plus 1, Cs plus 2, Cn, such that the first S columns together with this Ci is linearly independent. So, thus we take, so up to that is okay. Now, suppose, that means your S plus 1th column is Ci, right. Now, there are no conditions on S and S except S less than R. Suppose if S plus 1 is equal to N, that means S plus 1 is equal to N. That means there are S plus 1 columns. The columns are already over. C1, C2, Cs and Ci, these are S plus 1 columns are over. Then there is no column left which will be linearly dependent with the first S columns. Agreed? S plus 1 is N. That means C1, C2, Cs, S columns, and this Ci, N plus 1, which is linearly independent. And if S plus 1 is N, you have come to the end of the columns. There is no other column left. So there does not exist a column to be linearly dependent with the first S columns. Agreed? So this shows that the option 4 does not hold in general. In general, it is conditional. In general, it is not true because there are no other conditions given except S less than R. Therefore, this option does not hold in generality. So that and the answer for this question is option 1 and option 3 are true. And that is the detailed discussion of the solution of the problem from the section linear algebra on the concepts of the rank. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.